feel like there was a couple things last time that we didn't quite get to finish talking about. So let's real quickly talk about exponential and logarithm functions. That was kind of the last thing on my list of pre-calculus topics to cover. This is a reminder. If I ever get off screen, just tell me I'm off screen and I'll move things around so it'll be on screen. Those of you on Canvas on Zoom as well, feel free to let me know. Hopefully you can hopefully things are in focus here. All right, cool. So exponential logarithmic functions. I don't have a whole lot to say about them. Here's kind of the basics. So for exponential functions, they look like this. I'm going to go your basic f of x equals 2 to the x. That's kind of your most basic exponential function. And it looks like the following. An intercept of 0, 1. And some features of this function. Its domain is everything. All real numbers. Its range, on the other hand, it's not everything. It's all positive numbers. It has a y-intercept of 0, 1. Does not have an x-intercept. And it has a horizontal asymptote of y equal to 0. Question?
Is there any formula for finding the horizontal asymptote of any function?
I wouldn't say there's a formula, I'd say there's a process. And so the process of finding a horizontal asymptote is actually taking the limit as x either goes to infinity or to negative infinity. So for this graph, we can see that to the right, the limit as x goes to infinity of 2 to the x is infinitely large, right? If you have 2 to a higher and higher and higher power, it's going to get bigger and bigger and bigger. So we do not have a horizontal asymptote to the right. On the other side, if we look at the limit as x goes to negative infinity of 2 to the x, well, then you're getting 2 to the negative infinity, which I am never a fan of negatively large powers. They just don't really track well in my brain. So what I usually do when I have a limit like this and my exponent is a negative large number, I like to reframe things. I'm going to rewrite this as the limit as x goes to negative infinity of 1 over 2 to the negative x. And the reason I do that is so that now I can see I have a positive exponent. I know it looks like there's a negative sign there. There is a negative sign there, but I have a negative negative, right? So I can see, oh, look, this exponent here, negative x, that's getting large. 2 to a large number is also a large number. 1 over a large number is a, let's see, small number. So this rational expression here is getting smaller and smaller and smaller. It's getting closer and closer to 0. So this limit is 0.
In this case, we have the graph. What if like you have a function like a rational function? Would there be like any way to know which limit to take?
It's this one. So when we're talking about horizontal asymptotes, you're always, so when someone says what is the horizontal asymptote of this function? Is there a horizontal asymptote of this function? They're asking about behavior. They're asking about what is the behavior of this function as you go way that way or way that way. And the way we find that behavior is always by taking this limit. Now, there are other kind of shortcuts, but at the end of the day, this is what it all kind of goes back to. You can always find a horizontal asymptote by looking at the limit to infinity or the limit to minus infinity.
If our horizontal asymptote was something like y equals 3, sorry, x equals 3.
That's a vertical asymptote.
Y equals 3.
Y equals 3.
It's the horizontal.
Correct.
That would, the limit as we are approaching infinity would be 3, and approaching negative infinity would also be 3. It's going from different direction.
Correct. Yes. And we'll look at the rational function too as well, just to kind of clarify that. Was there a question over there or no? If I say raise your hand. Oh, sure. So can I clarify anything?
What's the inherent difference between the domain and range and the actual limit?
Sure. So domain is all the possible x values. And in this function, x can be anything, right? Because the only, again, when I'm thinking about domain, and we'll look at a couple examples. So let me write myself a couple notes here. Which is already on my mental list. When you're talking about domain, there's only kind of three things we try to look for to see if there are any domain problems, and that's either division by zero, or a square root of a negative, or a logarithm of a non-positive number. Those are the three main things. There's one other small subcategory of functions that we're not going to worry about. Those are the three main things. So if someone says domain, you look for those three things. Range, on the other hand, is all the possible y values. So in this function, the y values go as low as almost zero, but we never actually get to zero, and as high as you want. So our range is everything from zero, not inclusive, all the way to infinity. And then as far as the horizontal asymptote is concerned here, horizontal asymptotes can be a little tricky. I mean, we just talked about them a bit. They are what the function is doing. So really, when I say the horizontal asymptote is y equals 0, all I'm saying is as we move way out that way, the function gets closer and closer to 0. And I should also stress, because it is true, a function can totally cross its horizontal asymptote. They don't have to, but they definitely can. I'll give you a couple examples in a little bit here, but I promise you, a function, you can't cross its vertical asymptote. I mean, technically someone can make up something terrible that did kind of cross on vertical asymptote, but it's a little weird. But functions totally can cross their own horizontal asymptotes any day of the week. Horizontal asymptote doesn't care what's happening in the middle here. All it cares about is what's happening way out this way or way out that way. You guys seem like you don't believe. I see the look on your faces like you really don't believe me. So I'm going to give you an example right now. Yeah. Right. And that's not a bad way of describing it. It's just a little bit limited. So let me give you all an example. We'll come back to this in a moment here. So here is, let's pick an easy example, James. Let's say our function is, how easy? Yeah, let's not try to get too fancy. So our function is, sure, x minus 2 over x squared. X squared, yeah, why not? Plus 1. Okay, so this function, let's talk about all the things. It's a rational function. Rational function just means that it's a polynomial divided by another polynomial. Polynomial being powers of x that are non-negative integers, right? You can't have fractional powers, you can have negative powers, gotta have positive integer powers, or zeros. Okay, so let's find all the things. So, and we'll definitely come back around to this in chapter 4 of the textbook when we start graphing things like in earnest. But for now, this is how, if I had to graph a rational function, this is what I would do. Come on in, talking about rational functions. So I'm going to find all the things, meaning I'm going to find the intercepts and the asymptotes. So the y-intercept, I'm going to set x equal to 0. I'm going to get y equal to f of 0, which is negative 2 over 1. Cool. X-intercepts, set the whole thing equal to 0. And the nice thing about setting a fraction equal to 0 is you really only have to set the top equal to 0. Because for a fraction to equal 0, you need 0 divided by not 0. So really just, we're setting x minus 2 equals 0. You could also rationalize this to yourself by multiplying both sides of x. Right, multiply both sides by the denominator, you get x minus 2 on the left, you still get 0 on the right, because 0 times anything is 0. And then we end up getting x equal to 2. Okay, vertical asymptotes. So we find vertical asymptotes is by seeing where the function's undefined, by setting the denominator equal to 0. In this case, if we set x squared plus 1 equal to 0, we don't get any solution, right? X squared plus 1, x squared is always greater than or equal to 0. X squared plus 1 is always greater than or equal to 1. You could also keep going and try solving this, and you're going to run into problems. X squared equals negative 1. X is the square root of negative 1. I mean, technically, that's a thing. It's an imaginary number. We don't graph those on the real by real coordinate axis system. So No vertical asymptotes here. And lastly, we have the horizontal asymptotes, which we're going to find by taking the limit as x goes to infinity or negative infinity. I will point out that for rational functions, you get the same value either way. So if you have a rational function, you take the limit to infinity or a limit to negative infinity, you get the same result. Here's why. So to deal with this kind of limit, there's probably three different ways you can do it. One way you could do it is by using L'Hopital's rule later on in class, which we haven't learned yet. You might have learned before if you took calculus before. We're not doing L'Hopital's rule right now. It's out of our league. You can also use a shortcut here. There's some shortcuts for rational functions about how if you know the top power is less than the bottom power, you get something. If you know the top power and the bottom power are the same, you get something. But I'm just going to do it the way that's kind of the most, I don't know, the most easy to understand. I'm going to do the thing you always is the strong thing. You a lot of the time want to do for a rational function is you want to divide everything by x to the highest power in the denominator. So I'm going to divide everything by x squared. The highest power of x in the denominator. Let's see what happens. So if I divide everything by x squared, with the limit as x goes to infinity, and x divided by x squared minus 2 divided by x squared over x squared divided by x squared plus 1 divided by x squared. I'm going to simplify. I'm going to get, let's see here, the limit as x goes to infinity of, let's see here, 1 over x minus 2 over x squared over x squared is 1 over x squared. Okay, now here's the big question. This is kind of the big deal about this. As x goes to infinity or negative infinity, what happens to 1 over x? Does it get big or does it get small? It's small, right? If x is really, really big, 1 divided by a really, really big number is a really small number. So this is going to get really, really close to 0. What about 2 over x squared? Kind of the same thing. How about 1 over x squared? All those things that are divided by something that's getting larger and larger and larger, they all get smaller and smaller and smaller. So what am I left with? Well, I've got 0 on top, and I've got 1 on the bottom. 0 divided by anything that's not 0 is just 0, right? 1 goes into 0, 0 dies. So our horizontal asymptote is 0, which kind of makes sense if you think about the expression from the beginning. If you have x minus 2 divided by x squared plus 1, that denominator is getting larger faster than the numerator. That fraction, right? For example, if x were equal to 1,000, you're going to get 1,000 minus 2 over 1,000 squared, which is 1,000,000 plus 1. So you essentially got 1,000 over 1,000,000. That's a pretty small number. That's like 1/1,000. And the bigger x gets, the faster the denominator is going to outpace the numerator. So if your fraction has a bigger denominator than it has numerator, it's getting smaller. So the horizontal asymptote is the line y equals 0, aka the x-axis. We're doing it to find the horizontal asymptote. So the way, there's lots of ways to see, like for example, I will point out, you could have said, I know that the horizontal asymptote here is y equals 0 because the degree on top is less than the degree on the bottom. There's another way people know how to find horizontal asymptotes of rational functions. But at the very kind of base level, the way you can always find what the horizontal asymptote is by finding the limit to infinity and to negative infinity. Because that's what we're asking about, right? When you talk about horizontal asymptotes, you're asking what's happening as you go way out that way or way out that way. That's what that really means when you say, what's the horizontal asymptote? It's also another thing that you're asking about the end behavior of the function. What's happening way out that way. Also be 0, right? Because you're still dividing by a very, very large number. It just happens to be negative.
So if you have 1 over -1,000,000, it's extremely small.
Right. It's tiny bit negative. So maybe it's going to be slightly below the x-axis instead of slightly above.
Wouldn't be less
Well, so let's,
Oh, it would go this way, and that would go.
right, exactly. So for example, maybe just before I graph this one, just an example you probably are all a little more familiar with. A function 1 over x. Looks like this. Definitely has a horizontal asymptote at y equals 0. And we see that both the limit as x goes to positive infinity of 1 over x is 0 because we're getting very, very, very small. And the limit as x goes to negative infinity of 1 over x is also going to be 0. Because again, we're getting very, very, very small. And I will mention, as we go to positive infinity, we get closer and closer to 0, but we're still positive. And as we go towards negative infinity, we get closer and closer to 0, but we're slightly negative.
Could you explain that in terms of input and output? So our input is going to infinity and it's going to negative infinity, and output is reaching 0, right? That's what horizontal asymptote. And for vertical asymptote, how would that work?
So the vertical asymptote here, I'm going to find by just seeing where the functions are defined.
And that would be where we can't have a input that would give us any value.
Right. So really, and again, so the vertical asymptote here would be x equal to 0, but really it's also described in terms of limits. And again, we're kind of getting it, we're kind of putting the cart before the horse, getting ahead of ourselves because we haven't really talked about limits in depth here. But the idea is that you have a vertical asymptote when the function gets very, very positive or very, very negative. So really, the way we'd say this, and I'm going to back off this in a second here, is we would say we have a vertical asymptote here because the limit as x gets really, really close to 0 from the right-hand side, so from this side, what's the function doing? Getting really, really infinitely large. So we would say that this limit is positive infinity. And if we approach 0 from the other side, the left side, that function gets really, really negatively large. So you have vertical asymptotes when the function ends up getting positively infinitely large or negatively infinitely large. Okay.
So a whole is different.
Whole is totally different. So let's I know you all have lots of questions and they're good questions. Let's go back to this other example real quick because I did want to assure you that I wasn't lying to you. And then we're gonna talk about limits. Where'd my example go? Sorry. Oh yeah, here. So here's the function that we were talking about, and I kind of ran out of room to graph it, so I guess you can paper. So let's graph the thing and see all the important features on our graph. So let's see, we had a y-intercept of -2. We had an x-intercept of +2. We had a vertical asymptote of none, and we had a horizontal asymptote of 0. Okay, so here's how this is going to look. And again, this is maybe not the best graph ever, but I have an x-intercept right there. And I'm going to cross the x-axis. So if I look at my function for just a second, x minus 2 over x squared plus 1, that denominator is always positive, right? X squared plus 1, always positive. And that numerator is going to be positive if x is bigger than 2 and negative if x is less than 2. So this function is going to be positive over here on the right side of 2 and negative on the left side of 2. So it's going to look something kind of like this. Now later on, when we talk about derivatives, we will learn how to find this relative maximum here and this relative minimum here, but we're not concerned with that right now. What I want to show you is two things. One, the horizontal asymptote is definitely 0, right? The graph is getting closer and closer to 0 as we move way out to the right, closer and closer to 0 as we move way out to the left. And I crossed my horizontal asymptote. Totally something that can be done. Happens all the time. Sometimes it happens an infinite number of times. There are functions that can cross their own horizontal asymptote an infinite number of times. I'll tell you what it is, or one of them. Sine of x over x. It's got a horizontal asymptote is y equal to 0. And it crosses that an infinite number of times. Kind of cool. You should graph it on Desmos sometime.
And what was the purpose of, like, at least for myself, being originally taught that, like, the horizontal asymptote for most functions isn't cross?
Because it's an easy way to describe it. Because most of the time that is true. Most functions don't cross the horizontal asymptote. You're like, oh yeah, you just get really, really close to it. But technically, there are functions. So really, the idea is that the horizontal asymptote is a value that the function gets closer and closer and closer to. Right? You can, if you move far enough out in either that direction or that direction, you can get as close to the value that your horizontal asymptote is as desired. That's kind of the point.
So how does it work? They don't really approach one value at the end, they approach two different values.
Right.
So what's the horizontal asymptote for like sine of x?
Doesn't have one. Not every function has a horizontal asymptote. No, it has no horizontal asymptote because there isn't a value it is getting close to.
Because it bounces back.
Right. There is, right. The sine of x goes back and forth between -1, 0, -1, 0, -1, 0, 1, -1, 0, right? It doesn't get close to, and I'm really trying to emphasize this idea of closeness because it is super important for talking about limits. It's not getting close to any one specific particular value.
And also it does touch -1 and 1.
Right, which is totally fine.
So here, for example, the horizontal asymptote should not touch 0 at the end of this, right?
I wouldn't say that either.
Even at infinity?
This function, sine of x over x. Okay. Guys, I'm gonna make you believers. If Desmos will open here. There we go. Y'all can see that, right? On the Zooms. They've got things shared correctly. So if we graph, I mean, I'll even make it more fun. I'll add one to it. Sine of x. X, let's just add 1. Let's add 3. So that function has a horizontal asymptote of 3. Here it is. And if you zoom out, you will see that it crosses its, yeah. Look, it's crossing its horizontal asymptotes an infinite number of times. And no matter how far out to the right I go, it's going to cross 3 again and again and again and again and again and again. Yeah.
I'm so sorry.
No, the questions are good. Don't be sorry. I wouldn't say it's close to popular. Well, I mean, it would. But sorry, finish your question before I start jumping in.
Why is it considered a horizontal asymptote? Because it's cheating what the definition is.
Well, what's the definition of horizontal asymptote?
No, I was gonna ask another
Go
question.
ahead.
Because, what's it called? The limit of sine as you approach infinity does not exist. Because
Correct.
it oscillates. So
Correct.
why isn't this?
Yes. So we're getting there. So here's the deal. And this is where I really want to be very, very super specific. So if a function has a horizontal asymptote, we find it by taking the limit as x goes to infinity of that function, or the limit as x goes to minus infinity of that function. That is how a horizontal asymptote is defined. So that is the definition. All we're asking when we're saying what is the horizontal function is, as the x values get bigger and bigger, or smaller and smaller, negative and negative, what value is the function happening to get closer and closer to? Maybe crossing it a bunch of times, maybe not.
Do they have to be the same?
No, they don't.
Okay.
They most often are, but they not always are.
So one or the other would be sufficient for one horizontal
Right.
asymptote.
So there are functions that have two different horizontal asymptotes. One value to the right, one value to the left. Here's my favorite example of one of those. F of x equal to the inverse tangent of x. That function looks like this. Its horizontal asymptote is pi over 2 to the right, and negative pi over 2 to the left. Kind of interesting. Okay, there's other examples too, but that's like the easiest example to come up with. Okay, what's that? Go ahead. It is the limit, definitely the limit. So you could totally say for this function, the limit as x approaches infinity of the arctangent of x is indeed equal to pi over 2. And this piece of information definitely comes back in 21b for sure. Like that, someone's going to ask you about that in 21b, almost guaranteed. And the limit as x goes to minus infinity of the arctangent of x is negative pi over 2. Okay, and you had a question about sine x over x. So you're right. Sine x over x total. Let me make sure I'm not doing things too out of order here. Okay, yeah. All right, cool. So sine x over x, definitely sine x does oscillate, and its limit does not exist.
Oh, okay, so that makes it feel better then.
So the limit as x goes to infinity of sine x definitely does not exist.
Yeah.
Because sine x doesn't get close to one particular value. On the other hand, the limit as x goes to infinity of sine x divided by x is 0.
But it's been crossed it multiple times.
Okay, so I'm jumping all over the place, but it's fine. It's good. So why does this work? Well, we'll come back and see another example here, but check this out. Sine of x, you all know sine of x is between, what's the biggest sine of x can ever be? 1, and what's the smallest it can ever be? Okay, so now I'm going to try to make this look like that. So I'm going to divide everything by x.
So then, it just gets like closer to 0 in that case, like it oscillates in smaller. Okay.
Exactly. So what's happening here is because this limit is 0, and this limit is also 0. The thing in the middle is less than or equal to 0 and bigger than or equal to 0. It's got to be 0. This is a prime example of the squeeze or sandwich theorem. So because this limit's 0 and this limit's 0, we can say by the sandwich theorem, the limit of the thing in the middle is also equal to 0. 1 second. So we can also see it graphically. If I can get my thing back here. Check that out. Our function, sine x over x, is always between 1 over x and negative 1 over x, right? It's always below 1 over x here. It's always above negative 1 over x here. And so as those two things squeeze together, as you move further and further to the right, the thing in the middle is stuck between them and has to get squeezed to the value that they're both getting close to. It's kind of cool. It's kind of a great theorem. Other questions? Yeah.
So the textbook, I think it was in 1.3, if I'm not mistaken, give us two different visual inequalities for sine and cosine. For sine, it was negative absolute value of theta is less than or equal to sine of theta.
Sure.
Less than or equal to absolute value of theta. That's the one we use right now.
It's not. No. That's something else which we'll get to. That is that.
Know that because I didn't find any application for it.
We're going to.
Okay.
But not quite. It's definitely going to come up when we talk about the derivative of sine and cosine.
But that's not this.
That's not this.
Okay.
Negative line of negative 1 over x and this positive 1 over x are overlapping.
No, they're not overlapping. So let me draw it just because I know that the thing over there is not super extra easy to do. So here is 1 over x. Here's the right side of 1 over x. I'll draw the other side too. Here's the other side of it. Let's use a different color for the other one. Let's use, did I not bring my super fun colored pen? I left it in my office. Oh, well. Use boring colors. I guess that's all right. I got enough. But thank you. I appreciate the offer. So then here's -1 over x. And then stuck in the middle with you is sine x over x. So I know that sine of x equals 0 whenever x is a multiple of pi. So I just want to point out, right? Sine of pi is 0. Welcome. Sine of 2 pi is 0. Sine of 3 pi is 0, and so on and so on. So every time I hit a multiple of pi, I know I'm going to end up crossing the axis. And so it's going to look, it kind of looks crazy over here. I don't want to see, I don't want to worry about what's going on over there. I'm going to start here at 0 and be like, okay, well, I know that, let's see, and do something like this. It's kind of stuck. And we're stuck between those two functions. So that's, I mean, I know my picture is not perfect, right? It's definitely better on this, but that's the idea, is that we're getting smooshed as we go further and further out. Okay. Yes.
You should work for cosine as well, right?
Yeah, totally. Cosine x over x also equals close to 0 as you move out towards infinity. All right, so let's see. We talked about rational functions. We briefly talked about exponential. Oh, I know. I was going to go back. Let's talk about logarithmic functions just for a second, and then we'll really hit the limits super hard. So, logarithmic functions. I just want to kind of mention them because they have a great contrast with exponential functions. So, if you're thinking about f of x equal 2 to the x, and then we want to look at the inverse function, the logarithmic function, g of x equal to log base 2 of x. And the thing I would encourage you all to take to heart when it comes to logarithms and exponentials is they really undo each other. An exponential function takes some input, spits out some number, right? Well, really, I'm saying it kind of all backwards. What I really think of is the following. I know that 2 to the 3rd equals 8. I know that log base 2 of 8 equals 3, right? This function gives you a power, spits out the number. This function gives you a number, spits back the power. So when you're finding a logarithm, you're looking for the exponent. You're looking for the power that you raise this base to get that number. And literally, these two functions interchange the role of your input and your output. Right? In this function, you're inputting 3, for example, and you're getting out 8. In this function, you're inputting 8, for example, and you're getting out 3. So you have this whole literal reflective nature. So my logarithmic function looks like this. Yes, I can. It has all of the qualities of the exponential function, but interchanged x and y, meaning instead of the range being from 0 to infinity for this function, the domain is from 0 to infinity. The domain is all positive x values. And the range, well, in the previous function, the domain was everything. So now the range is going to be everything. And I want to very literally say we are literally interchanging the role of x and y. Right here, the x things is everything, the y things are 0 to infinity. Here, the x things are 0 to infinity, the y things are everything. We've even interchanged our intercept. We're going to interchange 0, 1 and get 1, 0. We've even interchanged our asymptote. Instead of getting y equal to 0, interchange x with y, and you get x equal to 0 for a vertical asymptote.
You think you could draw the exponential function on the x equal y so that would just
Totally. I was about to. Thank you for asking. So here's your inverse exponential function. And here is the line that they are symmetric about, y equal to x. And that is true for any pair of inverse functions, that they always have this graphical symmetry about the line y equals x. Literally, you could take this and reflect it over that line and get that.
you could elaborate a little bit about how is it that 2 to the log of base 2 equals just the x?
Sure.
So how do they cancel each other out?
So they cancel each other out in the way that all inverse functions cancel each other out, which is that they are literally defined to do that. But let's talk about why. So if f of x and g of x are inverse functions in y, I can't spell it, but you can see what that's supposed to say. Let's try it again. Inverse functions. Then you get the following. F of g of x has to equal x, and g of f of x has to equal x. Meaning, whatever you start with, one function does something to it, and the other function undoes that. And you get back to where you started. So for example, here are two inverse functions. F of x equal to 2x minus 3, and g of x equal to, so the nice thing about simple ones like this is you can literally talk out how to invert them. To invert a function in an easy function, you're gonna try to do the opposite things in the opposite order. So this first function here takes your input and first multiplies it by 2, then subtracts 3. So I want to undo that in the opposite order, meaning I'm going to first take my input and add 3, and then take that and divide by 2. There's my inverse function. They undo each other. So let's see what happens if I want to find, like, say, f of g of 7. Okay, we already know what the answer is. I'm going to show the work, but the answer is what? Right. But let's see what g of 7 is. G of 7 is 7 plus 3 over 2, which is 10 over 2, which is 5. And f of g of 7 is f of 5, which is 2 times 5 minus 3, which, surprise, surprise, is 7. So that's the very nature of inverse functions, is they undo what the other one does. And logarithmic and exponential functions are exactly that. They're functions that undo each other. So, for example, if I have f of x equal to 2 to the x and g of x equal to log base 2 of x, we can see that they undo what the other one does, right? F of, let's pick a different number. I'm not a fan of 3, but let's pick f of 5 is 2 to the 5th, which is 32, and g of 32 is log base 2 of 32, which is exactly defined to be 5, right? We're looking for the number you raise to get 32, which, oh yeah, that's fine. So how does the thing you're asking about work exactly? Well, let's go both ways. Let's look at the easier way, g of f of x, at least in my opinion, the easier way. Maybe you don't feel the same way, that's okay. Also, by the way, make sure you fill out the attendance form, scan one of the things, the plasticky ones, laminated, that's the word, thank you, the laminated ones. So to find g of f of x, I have g of 2 to the x, which is log base 2 of 2 to the x. So here's what this says. I mean, you can use a log rule here, right? So one, I won't say cheater way to do it, but one less, not what I really want way, is say, oh, the x can come down. You've got log base 2 of 2, and log base 2 of 2 is just 1, so x times 1 is just x. But the other way you could read this, if you want to be more wordy about it, so when I read log base 2 of 8, I think to myself, 2 to what power equals? So when I read log base 2 of this, what I'm really thinking is 2 to what power is 2 to the x? What, so 2 to the what equals 2 to the x? Right? It seems like almost a dumb question to ask because you've already said the answer. 2 to the x is 2 to the x. So that power must be x. Okay. The other direction is a little less nice. So let's look at f of g of x, which is 2 to the log base 2 of x. Okay, so actually I'm going to say the same kind of thing. let's look at this part here for a second. What is log base 2 of x? In very kind of generic terms, log base 2 of x is a number. In fact, actually, let's do a couple examples before I get back to this. So, papers. We'll do an easy example and then a less easy example, and then we'll come back to this. So here's my favorite easy example. What's 2 to the log base 2 of 8? And we know it's 8. But what's log base 2 of 8? And what's 2 to the third? Right. By the way, 8's my favorite number. So, I was born on 8, 8. You're going to see a lot of 8s. 8s all the time. Okay, so what about 2 to the log base 2 of 7? Oh, what the heck is log base 2 of 7? I don't know. I mean, it's something less than 3. It's 2 point something. But the point is, log base 2 of 7 is the number that we raise 2 to get 7. All right, that's what log base 2 of 7 is. It's a number that if you write log base 2 of 7 is the number that you raise 2 to get 7. Oh, look what we're doing. We're raising 2 to that number. You better get 7.
So on the top you're saying log 2 of 7 is the number to which if you raise 2, you get 7.
Exactly. Just like log base 2 of 8 is the number that if you raise 2 to that power, you get 8.
So how does 2 to raise into that power equal 7? That's the part I'm
Because we just said the words. So you literally just said the words that mean the thing that we want. So say it again. What's log base 2 of 7?
Log 2 raised to 7 is the number that you raise 2 to get 7.
Okay, so that's the number. That right there.
There's a number that we raise 2 to.
Oh, look, we're raising 2 to that number. What do we get? Ah, we get 7. So that, but it's tricky. Like I'm not trying to like say like you shouldn't like it's weird. Like you're like it's just it's like you're saying words that kind of circle back on themselves. You're like, oh, I just said the thing that's the answer, but it feels like I did nothing. Another way to see this, if you prefer, to say, well, if I want to find 2 to the log base 2 of 7, let's just call it some other number for a second. Let's call it y. And then you can either take a natural log or a log base 2 of both sides. I'm gonna use log base 2 because I'm already in log base 2. So we take log base, or actually I could really just rewrite it as a logarithmic statement. If I take log base 2 of both sides, okay, so what's log base 2 of 2 to some stuff? Oh wait, I can just bring it down, right? This power can come down in front. So I've got log base 2 of 7 times log base 2 of 2 equals log base 2 of y. And then the log base 2 of 2 is just 1. So I have log base 2 of 7 is log base 2 of y, but that means y has to be 7. That's another way that's a longer way to get there. I like what I did before.
So the word erase, I'm just trying to
Yeah.
rephrase it. The log base 2 of 7 is a number that we raise 2 to get 7, and we are raising 2 to that number, so we should get 7.
Exactly that. Yes. It feels very, again, kind of weird, but so now back over here, 2 to the log base 2 of x is just x. Because log base 2 of x is the number that you raise 2 to get x, and we are raising 2 to that number, so we get x. That's why it works out. And literally, it's because the logarithmic function is defined as the inverse function of the exponential function. Right? Someone said, I really want a function that undoes what the exponential function does. So they started with f of x equal to, I'm going to use 2 to the x again. And they said, oh, I really want the inverse. So I'm taking y equal 2 to the x, I'm interchanging x and y. And then I really want to solve for y. Since there isn't something that does that, they made up a new thing. So, well, I'm going to make something up. I'm going to say y equals log base 2 of x. And it literally means the same thing as x. I'm sure there is. I mean, there must, yeah, that's a good question. I'm not going to look it up. because I don't know. I mean, yeah, I don't know. I'm sure there's meaning that's beyond me, but yes. Okay, so logarithms. What time is it? 10:46. Okay. So I think we've done an okay job talking about those things. I'm always happy to talk about them. But I feel like we should start moving in the direction of talking more about limits, because limits are really kind of a lot of the basis for everything you're going to do in calculus. Maybe not everything, but certainly the first couple chapters is like limits. So let's look at some examples. Let's look at the following. Let's graph a function f of x equal to a piecewise function. It's x squared plus 1 when x is less than or equal to 0. X plus 1 when x is strictly between, whoops, that's not right. Between x and 3, and it is the square root of x plus 1 when x is bigger than or equal to 3. Okay, so let's see here. X squared plus 1 is an upward opening parabola, shifted up 1. So it's going to look like that. And it does, we do get the point x equal to 0, y equal to 0 plus 1. And it looks something like this. 0.01. And then y equals x plus 1 is a line that goes up from left to right, and it has a y-intercept also of 1. So it's going to also, it would have that point except to be an open circle, but it's going to be filled in by the other point there. And then it's going to go. So it's going to go to the point. It would almost hit the point 3, 4. So if I plug in 3 for x, I would get to that point there, except it's going to be an open point because x actually isn't defined to be equal to 3 there. And then the last part here, if I plug in 3 for x there, 3 plus 1 is 4, square root of 4 is 2. So I get the point 4, 2. And then it looks like the rest of a square root graph that kind of just goes off like that. So there's my piecewise function. A couple comments about this function before we start talking about it. It is definitely a not continuous everywhere function. And we can see that just by the nature of the graph, right? I had to, as people like to say, I had to lift my pen off the paper to draw the graph. I mean, I had to lift my pen off the paper anyway, because like it just needed to, but right, I couldn't have drawn this without lifting my pen off the paper. So let's talk about some limity type things. So what does y approach as x approaches 0 from the left-hand side? Well, sorry, one more time. So we're approaching 0 from the left. So I like to think about we're coming at 0, at x equal to 0 from this side, and we're asking what value is y equal to? 1. Now, the idea here is that we're not actually plugging in 0. Sometimes you can't, though. The idea is maybe you're plugging in a super duper small negative number. For example, you can think about, well, for example, f of negative 0.0001 is pretty much, well, let's see, I'm plugging it into this piece of the function, right, because that's when x is left of 0. And I'm getting, I don't really want to plug in negative 0.0001. I'm just going to say, well, 0 approximately squared plus 1 is going to be 1. Again, I'm going to say this probably 1,000 times. The idea of a limit is, I want to emphasize the closeness. Right? We were asking what is happening to this function as the x values get really, really, really close to 0. Oh, in this case, the y values are getting really, really close to 1. And yes, it happens to be true that when x is equal to 0, y is equal to 1 for this particular function. Okay. Of course, I never give myself enough room. Same question from the right. I guess this paper here. So what about from the right? What does y approach as x approaches 0 from the right? So here, we're going to get the same result, but in a slightly different way, because I'm going to pick a number a little bit positive, like 0.0001. And then I'm going to plug it into, sorry, not this top function here, because that's when x is less than 0. I'm going to plug it into this middle function here, because that's when x is bigger than 0. So I have to think about which piece of the function I'm using, depending on if x is positive or negative, or wherever it is in the domain. So here, f of 0.0001 is going to be approximately, well, instead of saying 0.000, I'm going to just say it's approximately 0 plus 1. So as x approaches 0 from either the left or the right, we're getting a y value that's getting close to 1. And yes, at 0, but it doesn't have to be. We'll see. Limit does exist, but again, I don't really, right? If I subtracted that point there and made it a whole, the limit would still exist. I'm going to say this too. The limit doesn't care what's actually happening at the point. The limit cares about what's happening very, very close, but not at the point. Just close to the point. Okay. So, a couple other things I meant right here. So here we would say the limit as x approaches 0 from the left of f of x is equal to 1. That is the notation for that. And again, all it means is as x is close to 0 from the left-hand side of 0, the y value is close to 1. And in a similar way, here we could write the limit as x approaches 0 from the right of f of x also equal to 1. And then, because the left-hand limit and the right-hand limit are the same, exactly what you said, the overall limit exists, meaning since the limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the right of f of x, that means the overall limit exists, or the two-sided limit exists. And we have that the limit x approaches 0 of f of x is equal to 1. So for a limit to exist, the left and the right-hand side limit have to be the same. In fact, we should write that down. So if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x is equal to some value. We often say capital L is the general limit value if we're just trying to make up letters. So if that's true, then we get to say that the overall limit as x approaches c of x is also. I guess we should take a break. I know I said so. Yeah, we should take a break. I'm gonna use the restroom. We'll take like a 5-minute break. Come back. We'll start at 11. Yeah. Okay, so let's. We're good. It's 11 o'clock. Let's continue talking about limits of this particular function. So the other thing I want to look at for this function is what's happening when x is getting closer and closer to 3. And so what we can see here is that, let me try and keep things in order here. Always struggle to keep things in order. If I want to, and I'm going to, so instead of writing all the little things, I'm just going to kind of be a little bit more concise about this. If I want to find, for example, the limit as x approaches 3 from the right of this function, what I'm thinking about is what's happening to this function as x is closer and closer to 3 from the right-hand side. Now, I could look at the graph, and I could label these points. This is the point not included, but I still label it 3, 4. This is the point 3, 2. I could just say, well, look at the graph. As x is closer and closer to 3 from the right-hand side, the graph is getting closer and closer to a y value of 2. But if I didn't graph it or didn't want to graph it, I could also look at the function and say, well, when x is defined to be larger than 3, the function is defined to be the square root of x plus 1. So I can say that's going to equal the limit as x approaches 3 from the right of the square root of x plus 1. Because that's the piece of the function I'm using when x is larger than 3. And then what we often do when we evaluate limits is we just toss the number in there, right? Because we're really asking is what's the square root of x plus 1 getting close to as x is getting close to 3? Closer and closer to 3, 3 plus 1 gets closer and closer to 4, and the square root of 3 plus 1 gets closer and closer to 2. I should say the square root of x plus 1 gets closer and closer to 2. Right, so we're getting closer and closer to 2, which means the limit is indeed 2. Oh, I could have shown another step there. Let me show one more step. It's equal to the square root of 3 plus 1, which is 2. On the other side, I want to find the limit as x approaches 3 from the left. I again could look at the graph and just be like, well, as x gets closer and closer to 3, the function is getting closer and closer to a y value of 4. Or I could just use the way the function is defined. When x is left of 3, it's going to be in this region here where x is just slightly less than 3. So it's going to be the limit as x approaches 3 from the left of x plus 1. And then I can just substitute in 3 for x and get 3 plus 1, which is 4. So I want to point out here, it's totally, what I'm saying is, I'm asking what is x plus 1 getting really, really close to as x is getting closer and closer to 3? Oh, x plus 1 is getting closer and closer to 3 plus 1, which is 4. So we say that this limit is equal to 4, even though the function doesn't actually get to the point 3 comma 4. Right? We're just asking what value does this function happen to be getting super duper extra close to as x gets closer and closer and closer and closer and closer and closer and closer to 3 from the left. Okay, so what this means for us as far as the overall limit is that the limit as x approaches 3 of f of x does not exist because the left-hand side and the right-hand side do not match up. The left-hand limit does not equal the right-hand limit. So that happens sometimes, right? If the left-hand limit and the right-hand limit don't match up, the overall limit doesn't exist. Question?
So all of this thing is treating your input approaching a specific value.
Correct.
Could you have a limit where our output
No.
approaching?
No, so the limit specifically says, it's asking the question, what is the function doing as the input is doing this thing?
So we couldn't have, for example, here limit as y approaches infinity, and wouldn't that equal?
No, we don't ask limit questions like that.
Different notation.
Well, again, the limit really, really specifically is a question about the function output behavior as the input does a thing.
So if you want the input behavior as output does something, would that
Be a totally different question.
Okay.
Right. It would be kind of, you have to ask about the inverse function.
Can you go back to the graph and just verbally walk through like each of them?
Totally, yes. So for the graph, we first looked at the limit as x approaches 0 from the left. And now I'm going to finally ruin my graph. As x approaches 0 from the left, we said that y was approaching positive 1. And as x approaches 0 from the right, the corresponding y values also approach positive 1. So that was this first limit as x approaches 0 from the left, x is 1. And then limit as x approaches 0 from the right, f of x is 1. And since those both matched up, we said that the overall limit was 1 because the left and right hand side matched up. And then the second one we just talked about was as x approaches 3. So when we do the limit as x approaches 3 from the right, we're saying, okay, x is getting closer and closer to 3 from the right hand side. And the function values are getting closer and closer to a y value of positive 2. And then the limit as x approaches 3 from the left, we're asking, okay, well, as x goes to 3 from the left-hand side, the y values are getting closer and closer and closer to positive 4. So the limit as x approaches 3 from the left of f of x is positive 4. And then since those don't match, that leads to us having a limit that doesn't exist.
Okay, so when you're exploring the limits, rather than like doing them in terms of like the functions that you had for the piecewise function, you're looking at them in terms of like the inequality bounds that you have within it.
Well, okay. So the thing that the inequality is giving me is which piece to look at. So if I'm looking at the limit as x approaches 3 from the right-hand side, if I'm on the right-hand side of 3, am I bigger than 3 or smaller than 3? Bigger than 3. I'm on the right-hand side of 3. Because right, the number line, right's bigger, left is smaller. So if I'm looking for x being bigger than 3, I have to go back to my piecewise function and say, okay, well, which of these pieces is where x is bigger than 3? Oh, it's this last piece here. And so that's why for that one, right, I used that piece. I said, oh, I'm using that piece there, and then just plugging in 3, getting that. On the other side, when I was approaching 3 from the left, that's when x is less than 3. Now, I've seen people get a little confused with this in the past. They say, well, James, x is less than 3. It could be this first piece or the second piece. Because technically, those are both where x is less than 3. And I would say, you're right. But then I would say, really what we mean when we're saying x is approaching 3 from the left is we are less than 3, but we are getting very, very close to 3 from the left-hand side. So if that's the case, we have to be this middle piece where x is between 0 and 3. So that's why when we do the limit as x approaches 3 from the left, we end up using that middle piece there. Because x is just less than 3. Good question. Other questions? Yeah.
Really quickly. So since our function is defined as a piecewise function, if we want to make the transformation, let's say we want to get the inverse of it.
The inverse is not particularly well defined here. I mean, you could find the inverse, but it's not something we really want to do.
Not specific for this function, but like any function that we have that's a piecewise, and let's say it was invertible. If we wanted to get the inverse, would we get the inverse of each function and just put it in, or would there be a different process for that?
It's not well defined. It really, there's not a good way to always do it, is what I would say. I saw another hand over here. Yeah.
Are they going to want us to work it out, or can we just see that it's like a jump function and that it's not?
It really depends on the instructor. So someone might say, like, tell me where the limit doesn't exist and why. If they said why, you'd be like, well, because the limit from the right is this, the limit from the left is this, they're not the same. But you could also say, like, maybe right now, like, I see that there's a jump, maybe the limit doesn't exist. So I can't really answer that fully because different people have to. I would always encourage erring on the side of giving more information rather than less. So if I would ask about this, I would have to be like, oh, the limits from the left and from the right are not the same. So I know I have a limit that doesn't exist there. Let's do some more examples. Yeah, let's keep things in order. Oh, actually, one last example from this one. So what if I asked about the limit as x approaches -2 of this function? Look back here. -2, which is probably like over here. So for that part, although I certainly could look at the left and right limit, I don't really need to because the limit or the function is defined the same way, immediately left and immediately right of the function. So while we certainly could do that extra work, we really don't need to. We can just say the limit as x approaches -2 of f of x is the limit as x approaches -2 of x squared plus 1, because that's the piece we need to use when x is getting close to -2, right? That's if x is close to -2, we're definitely in the less than 0 portion of the graph. And so then if I plug in -2, I get -2 squared plus 1, which is just 5. So again, what we're saying here is as x is getting closer and closer to 2, use a different color here, from either, sorry, -2, either from the left or from the right, the graph is getting closer and closer and closer and closer to that y value, which should be +5. My graph might not look like it's +5. So if the left and the right-hand side of the function are the same about the point you're looking at, you don't have to do a left and a right. I'm assuming the function. Okay, so more examples. So let's look at this next one that we're not going to graph because it's just kind of gross. F of x equal to x cubed plus 2x when x is strictly less than 1. the cube root of x plus 5 when x is bigger than or equal to 1, less than or equal to 8, and x minus 1 when x is bigger than 8. Okay, so let's first ask ourselves, what is the limit as x approaches 1 of f of x? Well, to look at that, I need to look at both sides, right? Because there's different things happening on the left side and the right side of 1. So maybe the limit's going to exist, maybe not. Yeah.
Left and right of like the different values. So for each of the pieces of the function, do we look at like the bounds of the inequality and then look at that in terms of left and right? Or like what is?
So here's what I would say. I would say I'm not so much thinking of this as an inequality. Oh, I mean, technically, yes, it is written as inequality. This is really just telling me the domain of the function.
Yeah, but I'm saying when I meant like the bounds. So like when we're talking about left and right, is it just within that context of like the that restricted domain? Like when you're saying left and right, like what is?
So when I'm saying left and right, I'm specifically referring to the limit. So I'm looking at the limit and saying I want to look at the limit as x approaches 1. I have to look at approaching 1 from the left side of 1 and from the right side of 1. Not for each of the functions. So the thing is, where I'm approaching from determines which piece of the piecewise function I get to use.
Okay,
So if I look at the left side limit, something in the limit as x approaches 1 from the left. Okay, left of 1, bigger than 1 or less than 1? Less, right? So it's easy, right? Left starts with L, left starts with L, left is less, and then right is 1. So if I'm approaching 1 from the left side of 1, I need to use which piece? The first piece, the second piece, or the third piece? It needs to be the first piece because that's where x is less than 1. So I'm going to use this piece. So the limit as x approaches 1 from the left of f of x is the limit as x approaches 1 from the left of x cubed plus 2x. And then, since it isn't a problem, I can just substitute in the value of 1. Because I'm saying if x is getting really, really close to 1, well, x cubed is going to get really, really close to 1 cubed, and 2 times x is going to get really, really close to 2 times x. So we're just going to use what's called the direct substitution property. Or in other words, most of the time, if you're trying to find the limit, you can just plug in your value for x. On the other side, if we want to find the limit as x approaches 1 from the right of f of x, that's going to be the limit as x approaches 1 from the right. Okay, so which of these pieces is when x is just to the right of 1? Is it the first piece, the second piece, or the third piece? It's going to be the second piece, right? That's where x is just a little bit bigger than, or maybe even equal to, but I don't really care about the equal to part. I care about the bigger than part. X is bigger than 1 there. So that's going to be the limit as x approaches 1 of the cube root of x plus 5. I'm just going to plug in 1. The cube root of 1 plus 5. Cube root of 1 is 1. I think it's 6. And now we can answer the question. What is the limit as x approaches 1 of f of x? I mean, we can answer the question in a very unsatisfying way. It doesn't exist. So the limit as x approaches 1 of f of x does not exist. And because the limit from the left and one from the right are not the same.
Can you also solve it by like setting the first equation equal to the second one? And if like they don't equal each other, then it
Well,
exist, and it does.
by setting equal to, do you mean like setting x cubed plus 2x equal to the cube root of x plus 5? Or you mean setting like 1 cubed plus 2 times 1 equal to the cube root of 1 plus 5?
First.
So the first thing is that will kind of tell me where those things might intersect. I feel like you could do that, but you would be doing more work than you need to. So really, I mean, I will say what people often do, which is kind of not showing all the proper work, but still right way, is what people usually kind of do is they just say, well, I'm going to plug in 1 here and 1 here. If they're the same, the limit exists. If they're not the same, it doesn't exist. But I really would encourage you to show this work of finding the left and the right hand limits, because it's the thought process that you want to be getting into. You want to be thinking, oh, I'm not really plugging in 1. I'm saying what's happening as I creep up on 1 from the left, or as I get towards 1 on the right. right? I don't want to actually plug in that value because what we're going to see shortly is you're going to plug it in and it's not going to work.
Whatever number they're asking for, we look for either side of it. And then from given that, we look at what from our piecewise function satisfies what we're looking for, and then we solve for the limits from there. And if they're not matching, then the limit doesn't exist.
Yeah. Yes. Right. I did, yeah. So we're working towards that. But yeah, what we're going to see eventually is a lot of times when you plug in the x value that you're approaching, you get like 0 divided by 2. That's what we're going to get to eventually. We're trying to work up to that by saying, I really want to stress, emphasize the nature of the fact that when you're finding a limit, you're just asking what's happening if x is close to this number from this side or from this side or from both sides. So let's look at one other limit here, maybe 2. Let's look at what's the limit as x approaches 8. Of f of x. Okay, I want you all to write down what the left-hand limit and the right-hand limit are. So limit as x approaches 8 from the left of what thing should go here, and the limit as x approaches 8 from the right of what thing should go here. Fill those both in. So if we're approaching 8 from the left, we should be using the piece of the function where x is less than 8, which is this middle piece. So the limit as x approaches 8 from the left should be the limit of the cube root of x plus 5. And as we're approaching 8 from the right, it should be where x is larger than 8. So we should be doing the limit as x approaches 8 from the right of x minus 1. And then we can evaluate both those limits simply by plugging in our x value. So I'm going to get here the cube root of 8 plus 5, which is 2 plus 8, which is 2 plus 5, which is 7. And here I'm going to get 8 minus 1, which is also 7. So here, the limit does exist because the left and the right hand limit are both the same, and we have a match. So we get to say, oh, the limit as x approaches 8 of f of x, in this case, is 7. Because the left-hand limit and the right-hand limit are the same value. Whereas in the previous one, limit did not exist because the left-hand limit and the right-hand limit were different values. Yeah.
On the right function, is the function in place for
So no, so you can write this way. You can also write it this way. They mean the same thing.
So I understand what we're doing now, but in terms of like looking at like the whole function, like hypothetically, if we were to graph this.
Yes.
So this limit right now, does that count for the entire function, or is that just for the 2 pieces of the function?
It was really just for this one moment of the function, just when we're getting close to 8. So I don't know exactly what this function looks like, but I can tell you the following. I know that if I were to graph it, I know that as I approach 1 from the left, it's getting closer and closer to 3. And it's going to be not defined there. And it's approaching 1 from the right, it's getting closer and closer to 6. And so I'm thinking it's looking something, and then 8's over here. My graph's going to look stupid, but don't worry about it. It's going to look 7, sure. So it's going to look something like this. And then, I don't know, something funky like, I'm just making stuff up now, really. Maybe it looks like that. And then after 8, it looks like x minus 1. So it looks like that. So that's kind of what this graph looks like. But kind of, right? Don't like quote me on it. And we can see that as you approach 1 from the left versus 1 from the right, the limit values do not match up. Whereas we approach 8 from the left, 8 from the right, the limit values do match up. They're both getting closer and closer to 7. But again, we didn't need the graph to be able to answer those questions. It's nice to see the graph. Yeah. Okay, so let's look at some more examples.
Look at to understand like the relationships of everything.
Well, I mean, so it really depends. Like someone typically, if I'm giving you a piecewise function, I'm often asking about what's happening at the breakpoints. So as I move from this first piece to the second piece, right, that's happening when x is equal to 1. So that's where I'm usually interested in asking about the limit. And also when x goes from this piece to this piece, so x equals 8. So that is why I asked about those 2 points, because they're kind of the most usual suspects there. Yeah.
You can go over this Squeeze Theorem in this class.
Definitely. In fact, I think you actually missed, we talked about it a little bit earlier. We are going to talk about it again, but yes, we will definitely get to the Squeeze Theorem maybe today. We'll see. Definitely on Thursday, if not today. So let's look at this example. Let's find the limit if x approaches 9 of x squared minus 10x plus 9 over x minus 9. And now here's what we've been dreading. Or maybe not dreading. If you try plugging in x here, what do you get? Well, not only do you get division by 0, you get 0 divided by 0. Because if you plug in 9 at the top, you get, let's see, 9 squared is 81 minus 90 plus 9. That's looking a whole lot like 0 over 0. So which is not a real number, right? This is what's called an indeterminate form. We have to put this in quotes because we don't really like it. Indeterminate form.
This is where we use the negative infinity, the positive infinity, right?
Not necessarily. You might end up using an infinity. Well, actually, here's what I would say. Typically not. You typically end up getting a plus or minus infinity if you have a non-zero number divided by 0. So just,
Okay.
we're not going to do this one, but I'll just point out, if you were doing like the limit as x approaches 3 of 2x over x minus 3 squared, and you plug that in, you get 6 over 0, and that's where your limit would be some sort of infinity. We'll get there eventually. So here what we do, we do some algebra. So this thing, we can factor that numerator. X squared minus 10x plus 9 factors as x minus 9 times x minus 1 over x minus 9. And now here's the thing that people sometimes have issue with, which I'll try to explain as well as I can. I can cancel those x minus 9s. And here's where I want to revisit what I said a few times already. The limit doesn't care what's actually happening at 9. Limit doesn't care at all, right? At 9 is not in play at all. What the limit cares about is what's happening. It's really, really close, but not equal to 9. So let's say x was 10. If x is 10, and I plug it in here, 10 minus 9 divided by 10 minus 9 totally cancels. Totally fine, right? And then 10 minus 1 is 9. Or if x was 9.1. I want you all really to look at this, right? If I plug in 9.1, 9.1 minus 9 divided by 9.1 minus 9, those still cancel out, right? As long as I'm not plugging in 9, which I didn't want to do anyway, because the limit doesn't care what's happening at 9, those cancel. And so as long as I'm really, really close, but not equal to 9, this expression, I should say this expression and this expression are the same. Because they're the same everywhere except 9. The limit doesn't care what happens at 9. So now I can take this and just say, well, plug in 9. So this limit is 8. Let's talk about what's happening graphically. So if I want to graph a function, I'm going to write it as x squared minus 10x plus 9 over x minus 9, which is really just this, as long as x doesn't equal 9, because 9 would be a problem. Right? This is a graph where x can't be one value. Anywhere else, x is fine. Literally, right? If I make a table here of x values and x minus 9 times x minus 1 over x minus 9, I'm really just going to ignore the x minus 9s in my head. So if x is 0, I'm going to get 0 minus 1, which is minus 1. If x is 5, I'm going to get 5 minus 1, which is 4. If x is 8, I'm going to get 8 minus 1, which is 7. If x is 11, I'm going to get 11 minus 1, which is 10. Because the x minus 9 over x minus 9 part will always cancel out. Even if x is like 9.1, I'm going to get those canceling, and 9.1 minus 1 is 8.1. So this looks like the line y equals x minus 1. But I'm missing a point. That's what the graph of this looks like. It's the same as the line y equals x minus 1, except we have to take away the point when x equals 9, because if you plug in 9 here, it's totally undefined. But if you plug in any number super close to 9, like 9.000, all the zeros you want 1, if you plug in 9.000 zeros 1, I get 9.0001 minus 9 divided by 9.001 minus 9. Those cancel, and I'm left with 9.001 minus 1, which is 8.001, which is like right there.
So I get what you were doing there, and I don't know if it was completely turned out and missed something. But for the one with x is going to be toward 9, and so the x minus 1, because that's what we were left with. So why did you plug in, like, for finding the limit, why did you do 9 minus 1? Like, what was?
Well, because I would, so just like in the previous ones, right? All I'm doing is I'm taking my expression, like here, right? The limit as x approaches 1 and the keyword of x plus 5, and I'm substituting in the 1 for x.
Oh.
That's all I'm doing here, right? I'm just taking the 9 and I'm plugging it in for the x. But I couldn't have done that up here. So if I did it up here, I would have gotten that, which is a problem.
So a hole is defined as the place where the y is defined, but the limit exists.
Essentially, yeah.
So if that's true for any case that we have a hole, right?
Typically, yeah.
So how about the piecewise function? Would that be considered?
Not the piecewise functions. I mean.
So for continuous functions that have a hole, the hole is defined as a place where the limit exists. But
well, I wouldn't say it's a continuous function.
how could they define the hole?
So I would say typically a hole is a place you're going to get where some factors cancel. So usually it's a rational function. Usually it's something like this, where you've had some factors that cancel. So the place where if you plug in x, you would have gotten 0 over 0, and you can cancel those factors, and when you do, you then get a nice value.
So hole is where the function equals indeterminate form, which
Exactly.
is 0 or 0 over infinity over infinity. Is that also correct?
Yeah, it could be infinity over infinity, but you're less likely to get that.
And for this one, for example, if we couldn't factor it out, if there was no way to cancel out the bottom or the top, we would have to use the opposite rule. Is that the only way to solve it if it wasn't factorable?
It depends. It's hard to answer that. It's a very general question. So it does factor. So I can't really say like if it didn't, what we would do.
There's no one way to solve it.
Correct. There is no one way to really solve anything. Do you have a question? I thought I saw you raise your hand. Sorry. Okay. So let's look at another example. So let's say we want to find the limit as x approaches 2 of 4x squared minus 3x minus 10 over 6x squared minus 12x. Now, here's what I'll say about limits in general. If someone says find this limit, the first thing you should do is always just try plugging in x, right? A lot of the times it's not going to work, but don't let yourself get out of the habit of doing that, because people are going to be like 0 over 0, 0 over 0, 0 over 0, 1,000 times 0 over 0, and then they're going to be like 0 over 5, and the answer is just going to be 0. And you're going to try and do all this factoring or whatever, and then you're going to be like, oh, I could have just plugged it in. So make sure you at least think about plugging it in and seeing what you. So if I plug in 2 here, I'm going to get 4 times 4 minus 6 minus 10 over 6 times 4 minus 12 times 2, which is definitely a 0 over 0. Okay, so here's the great thing about polynomials. If I plug in 2, I know this is a rational function, but like the top of the polynomial is not polynomial. If I plug in 2, that means x minus 2. Sorry, if I plug in 2 and I get 0, that means x minus 2 is a factor. So I know for sure. Well, the bottom is going to factor pretty nicely anyway. Let's deal with factoring the bottom first. So what can I factor out from the bottom? I think I can factor out a 6x. I'm left with x minus 2. I know I want that x minus 2 factor to cancel. That's the thing that's causing me problems. So I know it needs to be a factor in the top. So that's why I'm going to start with x minus 2. I know x minus 2 has to be a factor for things to work out. Why do I know that? Because when I plugged in 2 to the top, I got 0. That's like the fundamental theorem of algebra. Like if you plug in the number to a polynomial and you get 0, that means x minus that number had to have been a factor. That's all I'm doing here. Saying, oh, I plugged in 2, I got 0. X minus 2 has to have been a factor. And then we can kind of work out backwards what the other pieces have to be. If this top thing is going to multiply to 4x squared minus 3x minus 10, well, x times a 4x is going to give me the 4x squared, and minus 2 times positive 5 is going to give me the minus 10. And then I can check the middle terms. Let's see, minus 2 times 4x is minus 8x, 5 times x is 5x, and minus 8x plus 5x gives me the minus 3x middle term, like I should have gotten. It always works. If you know plugging in something made your polynomial equal to 0, then that means x minus that something had to have been a factor. So you can start with saying, I know what I want, I'm just going to write it. And then we cancel those. We're left with the limit as x approaches 2 of 4x plus 5 over 6x. And then we just throw the 2 in there. You get 4 times 2 plus 5 over 6 times 2, which is what, 13 over 12. And so this graph would, if you were to graph this, I'm not going to graph it, but if you were to graph it, it would look like the graph of 4x plus 5 over 6x, which is some rational function, and it would have a hole at x equals 2. Yeah.
So if we wanted to find the limit of x up to 0, we would divide it by x.
I would not.
You would not.
So if I wanted to find, well, no, I would not. I would divide everything by x squared, probably. Limit as x approaches 0 is problematic here, though, because if you plug in 0, what do you get? 0 is like the only other problem place here. If I plug in 0, I get 0 minus 0 minus 10 over 0 minus 0. What's negative 10 divided by 0? Undefined. We're going to see this a little bit later. This is where you get a vertical asymptote. So if you end up getting a non-zero number divided by 0, you get some sort of vertical asymptote.
So to solve this one, we would have to know rules that come later.
Right, exactly, yes. Sorry, I keep seeing phantom hands. Like, I don't want to miss anyone. If I don't see your hand, you just say James.
Yeah, you know this one has a vertical asymptote again?
Because of how this looks. Because when you get a non-zero number divided by 0, you're essentially getting something that's infinitely large.
Yeah, I got it.
Right? I'm taking negative 10 dividing by a very, very, very small number. It's getting really, really, really big. Yeah. That comes later. I mean, still like not much later. Like it's like in the next section.
But it's negative infinity.
I can't. I don't know that it's actually negative infinity. It might be positive infinity. Because I don't know if that denominator is a little bit negative or a little bit positive. So that's actually the trick for the fine. Okay, like we've said enough about it. So here's what I would do if I was actually trying to find this one. I would say, well, I'm going to factor that denominator. I don't really care about the numerator. I factor out the 6x times x minus 2. So actually, this is going to be different on the right and the left of 0. So let's look at the left side of 0 and the right side of 0 real quick. Okay, so if I pick a number slightly positive, you should think 0.001. And I plug that in. Well, the top doesn't care. The top is still essentially -10. Because you've got something close to 0, minus something close to 0, minus 10. In the denominator, you have a number close to 0, but slightly positive. And then a number close to 0 minus 2. So if you take those two numbers and multiply them together, are you getting something slightly positive or slightly negative? Slightly negative, right? Because it's a slightly positive number times a number that's minus 2, essentially. So it's essentially a very slightly negative number. Yes, this has a vertical velocity at 0. And a negative divided by a negative is, and it's positive infinity because, again, right, if you divide by a really small number, your fraction gets very large. If you divide by a big number, your fraction gets very small, right? It's an inverse relationship. On the other side of things, here if I plug in a slightly negative number, the top is still -10, essentially. And the bottom is a slightly negative number times another negative number, which is going to be a slightly positive number. So this one ends up being a negative infinity. So graphically, here's what this would look like. I don't know what's going on with the rest of the graph, but I know that if I approach 0 from the left, I'm going downwards towards negative infinity. If I approach 0 from the right, I'm going upwards towards positive infinity. I know there's other graphs to the left and right, but that's what's happening in my vertical velocity. Okay. Let's look at a couple more not vertical velocity examples. Yeah.
So for the asymptote approaching infinity, going from the right is always.
Wait, what's approaching infinity?
Depends on asymptote.
Okay.
Approaches infinity.
I would say the vertical velocity is equal to infinity.
Okay.
Right, because when you're saying approaching, usually you're saying x is approaching something, and then the limit is the output value or infinity in this case.
Okay, so the graph of 1/x approaches infinity and negative infinity. The one going from the right side is always going to be positive infinity, and one going from the left side is also going to be negative infinity.
For that particular graph, yes, but not for every graph.
So if it was 1/-x, it would.
Sure, there's lots of different things that can happen.
Okay.
So let's look at this next example. Let's look at the limit as x approaches 3 of 2x squared minus 5x minus 3 over x cubed minus 27. And I do a quick mental check. 2 times 9 is 18, minus 15 is 3, minus 3 is 0, over 27 minus 27 is also a 0 over 0. You should check though, right? Because sometimes something can be like, fooled you. All right, so I plugged in 3, I got 0 over 0, meaning what should be my factors for sure on top and bottom? X minus 3. I definitely should have an x minus 3 on the top and an x minus 3 on the bottom. Okay, I need to fill in the rest. So on top, I need, let's see, I need something times x to give me 2x squared, so I need a 2x. And something times -3 to give me -3, so I need a +1. Kind of nice how that works. X minus 3 times 2x plus 1, and it does work. Right? If we check, I get -6x plus x, that's a -5x. Cool. The bottom, difference of cubes. So I'm just going to, well, I would like to show you all this real quick. So if you have a cubed minus b cubed, it's going to be a minus b times a squared plus ab plus b squared. And if you have a cubed plus b cubed, you can factor a sum of cubes as well. It's a plus b times a squared minus ab plus b squared. There is an acronym for this called SOAP. The sign is the same sign, the opposite sign, and always positive. Kind of cool. It works. If you're factoring a difference of cubes, I'm seeing this as x cubed minus 3 cubed. And x cubed minus 3 cubed is going to factor as x minus 3 times x squared plus x times 3 plus 3 squared. Or written more normally, x minus 3 times x squared plus 3x plus 9. And then we cancel the things that cancel. We plug in and we get 2 times 3 plus 1 over 3 squared plus 3 times 3 plus 9, which is 7 over 27. Cool. So a lot of the times when you have a 0 over 0, you're going to factor it. That's like my go-to first thing. Can I factor something? Can I cancel something? Great, I do it. But sometimes it's not going to work. Sometimes, we only have 8 minutes left. Okay. Sometimes factoring and cancel isn't the first thing you can do. Like you have the limit as x approaches 5 of the square root of x plus 4 minus 3 all over x minus 5. Definitely a 0 over 0 type. Right? If you plug in 5, you get 3 minus 3 over 5 minus 5, which is 0 over 0. But it can't factor. So instead, if you have something that has a square root, often the thing that we're going to do is we're going to multiply the top and bottom by the conjugate of that. The conjugate is just the same expression, except with an opposite sign in the middle. So the conjugate of the square root of x plus 4 minus 3 is the square root of x plus 4 plus 3. And there's a reason why we do this. And there's usually a reason. So I'm going to multiply by the square root of x plus 4 plus 3 over the same thing, right? Because the only thing you're really allowed to multiply by is it's just 1. It's just a interesting way of writing. Here's why we do this. It's going to get rid of the radical in the numerator, or in general, it's going to get rid of the radical in the place where it's the conjugate. So when I multiply out the top here, I'm no longer going to have any radical. Let's see what happens. Oh, I should also point out, I know I haven't said it, but until you actually find the value, it's really important to write the limit each time, right? If I didn't write the limit here, I would be meaning a different thing, right? Without the limit, that just says you've got some function. With the limit saying, oh, what is this function doing as x is close to 3? So make sure you write the limit in each step until you're actually plugging in the value. So, so if I multiply this out, I FOIL this out, square root of x plus 4 times square root of x plus 4 is x plus 4. And then square root of x plus 4 times 3 is 3 times the square root of x plus 4. Plus 4. And then negative 3 times square root of x plus 4 is minus 3 times the square root of x plus 4. And then negative 3 times 3 is minus 9. And notably, the middle terms are going to cancel. That is always what happens when you multiply by something by its conjugate. You get the first thing squared minus the second thing squared, and the middle terms cancel. It's really just a minus b times a plus b. Those are conjugates. You have the middle thing connecting them is the opposite sign. When you multiply that out, you get a squared plus ab minus ab minus b squared. Difference of squares. And then in the bottom, you don't multiply it. Or I should say, in the thing that it's not the conjugate of, you don't multiply it out. So I'm just going to leave the denominator as x minus 5 times the square root of x plus 4 plus 3. And the reason I don't multiply that out is I know that 5 is the problem. So I know that I want x minus 5 to go away. So multiplying that bottom part out is not going to help me see that. I want to leave the things that I know I want to cancel alone. All right, simplifying the top here. Let's see, x plus 4 minus 9 is x minus 5. So the limit as x goes to 5 of x minus 5 over x minus 5 times the square root of x plus 4 plus 3. Welcome. So I can cancel those x minus 5s now, right? That x minus 5 cancels that. I'm left with a 1 in the numerator. So the limit as x goes to 5 of 1 over square root of x plus 4 plus 3. And now that I don't have a 0 over 0 anymore, I can plug in the 5 for x. So I plug in the 5. I don't write the limit anymore. and 1 over the square root of 5 plus 4 plus 3, which is 1 over 3 plus 3, which is 1 over 6. Cool. Questions?
The value of the subclosure itself be a factor of x. Would be a case of the subclosure is 6 plus 1.
No, we really, when you're talking about limits, you're talking about x approaching a real value, not like a variable. Stretching? Okay. Oh, time is never on my side. Okay.
What's like the final notation for like boxing our answer? Like,
The answer is this number. 1, 6. I don't think so. You could, if you really wanted to, go back and write the limit as x approaches 5 of square root of x 4 minus 3 over x minus 5 equals 1, 6. I don't think you need to do that. Timing. We're not going to get to the squeeze theorem today. Sorry. Let's look at one more, maybe 2. Okay. Limit as x approaches. Yeah, let's do this one. 2 10 over x minus 5 over x minus 2. And as you'll notice here, this is also a 0 over 0 type. Big surprise. So here we can't really do any factoring either. It's not a square root, so it's not a conjugate kind of issue. What we need to do here is just use some common sense and get a common denominator. No, I know the reaching is like it's not going to be great. So there's a couple different ways to do this. I'm going to do it like this. I'm just going to do the common denominator at the top. So I'm going to say the limit x approaches 2 of, I kind of like that. Yeah. So I'm at 10 over x minus 5x over x. I don't love fractions and fractions. So what I would probably do in the next step is 2 things. I'd probably rewrite this as the top fraction as 1 fraction, right? That's why I got the common denominator. So I write it as 1 fraction. Write it as 10 minus 5x all over x. And instead of dividing by x minus 2, I would rather write it as multiplication by 1 over x minus 2. And when you're dividing by something, it's the same as multiplying by its reciprocal. Dividing by x minus 2 is the same as multiplying by 1 over x. And now I can do some factoring. Just a little. What can I factor out from 10 minus 5x? Yeah, so if I factor out a 5, I'm left with, let's see, 2 minus x. I might as well multiply these fractions together. 10 minus 5x times 1 is just the 10 minus 5x with the 5 factored out. And then the bottom, x times x minus 2, I'm just going to write as x times x minus 2. What's 2 minus x divided by x minus 2? Right. So there's a couple ways to see it. You can totally factor out a negative and say, and it doesn't matter really where you do it from. I'm going to do it from the top. So I factor out a negative 1 from the top. I'm going to have a negative 5 times, let's see, so that's going to be a negative 2 plus x over x times x minus 2. And those are the same. Right? They're written in a different order, but they are the same. If you really, really want, you can rewrite it. Make it look the same, but negative 2 plus x is the same as x plus negative 2, which is that. Those cancel. We're left with negative 5 over 2. One thing I will say is you're certainly welcome to factor out the negative here, but I want to make you aware of the fact that whenever you have things subtracted in the opposite order, they are always negatives of each other. So I could really quickly just say, I know that 16 minus x over x minus 16 is always going to be negative 1, unless x is 16. Because when you subtract things, right, what's 3 minus 7? What's 7 minus 3? And when you divide those, you get negative 1. It's true for whatever numbers you pick, as long as you're not getting 0 over 0. So whenever you have something minus x over x minus the same something, you can always be like, oh, I know that's going to factor and cancel for me. All right, that's all for today.